Okay, students, welcome to video class 11. And in this session, we are going to start with module 2. And the module 2 is all about time domain analysis. Time domain analysis of a system. Okay, so this is all about the time domain analysis of a system. And this is an introduction class to the time domain analysis, and we will be dealing the various aspects of time domains, just time domain analysis. Okay. Now, before going into that, we should know what is this time domain analysis. Say, you know, and when we talk about analysis of a system, we actually refer to a control system because we are studying a system in the perspective of a control system. So, if you have a system, say, as we have studied in signals and systems, this can be represented by, say, an input x of t, y of t with the transfer function t, right? So, okay, now by time domain analysis, it refers to we are giving some input, some known inputs in time domain to a system, and we will be finding out the response, and we call this as sometimes we may be calling this as an excitation, while this is called as a response. So, for some known or some standard inputs, we'll be analyzing the output or the output response of that system. And by studying the response, we will be getting some of the characteristics of that system, and that procedure we call as the time domain analysis of a system. So, if there is a time domain analysis, there can be another type of analysis called as a frequency domain analysis, and which is the major topic in module 3, and we will deal with that when we come over there. So, in this time domain analysis, this system will have so to start with, we will be dealing with some of the standard inputs that we can have to analyze a system, and from the analysis we'll be able to find out various characteristics of the system, and we call that as the time domain specification, or it is by those parameters we can specify a system, just as we purchase an electronic device. Say, for example, if you have a mobile, specification for that. So it is based on those parameters that system is designed for those parameters, or right. So similarly, a system can be studied in a time domain, so that we will be getting various characteristics of that system, and that will be referred as the time response specifications, and which we will be dealing it later in our classes. Okay. See, I just told you about something about the standard inputs. Those standard inputs are generally called as the test signals. And why the name test signals? Because these signals are used for testing an input or testing the input, so that we analyze the output. The test signals that we will be considering will be, say, unit step signal or step signal. Then you will be having a ramp signal or a unit ramp, and we'll be having parabolic input or unit parabolic input. So these are the three test signals that we will be using, and these are called as the test signals because they are used for the analysis, and you will be getting different responses for these inputs, and we will call those responses in the name of their inputs, and this response we call as a step response, meaning it is the output y of t when your x of t is u of t or unit step, and the response due to the ramp input we call as a ramp response, and the parabola, that of parabolic input, we call as a parabolic response. Okay, so the ramp response and parabolic response. Okay, so that is, and we will be dealing with this test signals and some of the frequency domain aspect which we have all studied in signals and systems. I will be just specifying, and I will be just having a recap of all those things which we have studied. Okay, now that's it. That's the test signals. Now, once when you apply the signals, you will be getting response, right? Now this response we call generally as y of t. Now when you analyze this response, you can say, for example, if a particular system you're analyzing, you are expecting an output of 5 volt, right? 5 volt. That is, this is the ideal expectation. That is, when you switch on, when you excite the input of, say, imagine this is the system where you give an input, some input, okay, some chest input, and you are expecting an output like this. The output at this should be 5 volt DC. That's our expectation, or that is the ideal case or ideal thing that is to be expected for any system. And what is the meaning of this system? Now, the ideal response, if this is the response of this particular system, we say that from the time t is equal to 0. What's the meaning of this? This is at this time t is equal to 0, the input has been applied. That means this response gives you an idea that at t is equal to 0, the output remains, the output switches to 5 volt even at the very moment at which when you apply the input. So that happens only in an ideal case. It won't happen in a practical case. Now practically, sometimes the system can, this is just a case, sometimes the system can rise above the 5 volt, and finally after some amount of oscillation, finally it can reach up to the 5 volt, right? So this is the practical way of the practical response of a system. You cannot expect a system to be 5 volt at the time of the input or the excitation. Okay, now so the different systems will be having different responses for the same input. So all these things can be studied, and based on that you can have the characteristics of that system. Now the next thing that we need to understand is when you look at the response, you can see this response can be divided into two, right? So look at this part, or rather, okay, this part. You can't say that the system has been settled to 5 volt because it is rising at every time it's oscillating, and after this time, more or less, you can say that the system has reached its desired value, right? That is the 5 volt. And that means this output state, this is actually the output. This output state can be divided into two states. That is the that is called as the transient state and the steady state, transient state and steady state, or this is the response, right? So the response can be classified as transient state response and steady state response. Okay, now up to this point the system actually is in a transition from, as the input is excited, it was normal. Now even before the application of the input, this was at 0. Now when you excite with a particular input, the desired value was 5 volt, but you are getting a graph like this, meaning it's not coming exactly at 5 volt at the time of t is equal to 0, but later on we can see that it is oscillating around 5 volt, and finally after some time, this is the time axis now. So at t is equal to 0, the input is excited. At t, say for example, let us call it as t1. At t1, it is not 5 volt, it's oscillating, and say let us call it as Ts. At a particular Ts, we find that the system almost reaches the 5 volt, which is the desired value. Now after this time, you can call this system has reached what? The desired value, or it has been in the steady state. Now what is this state? This is a state where the system gets transited from the 0 state to the desired value. So based on this, any output response can be of two types, that is a transient state response and the steady state response. By studying the transient state response, we will be able to understand how far the system deviates from the reference input. So here in this example, this is the maximum change that can have from the reference value, right? So this is the maximum value. Okay, So this is one of the thing that we can study. And not only that, and how long will it take to settle to its steady state, that can also be studied by knowing the transient state response. And this can be, so this actually, this especially the settling time all depends on the components of the system, and by suitably selecting and designing those components, we can regulate this transient state response, right? Now, not only that, this transient state response will also give you an idea how much faster it can or how much slower the system to reach its steady state. The more the time it takes, that refers to that's a slower system. Okay, so it can be made faster by changing some of the components, as you have studied in your network theory regarding RC. RC is referred as a time constant. By varying this time constant, you can regulate the time that takes in the transient response and the steady state response. Okay, so all these things can be studied under the transient state response. Now, once the steady state has reached, what is the meaning of steady state? The meaning of steady state is reaching its desired value. For in this example, when the system reaches the 5 volt at its output, then we call that as, or it's near to 5 volt, we say that the system has reached its steady state. Now, even in the steady state response, there can be a slight variation from the output, right? And in such a case, there can be something called as error that results in the error, and this is referred as the steady state error. Steady state error. Okay. Now, this steady state error, as we will find later, this steady state error depends on the test input. So, for various inputs, the steady state error of the system varies, and based on that, you can restrict the system to some of the inputs. Say, for example, when we analyze, we will be able to find out for some inputs, say for some input, for unit step, it's okay, but when you give ramp, the steady state error may become infinity. So, in that case, we should have put a restriction to the input that is to be given. For a unit step, it's okay, but for a ramp, it will be giving a high error rate. So this can be studied by having this steady state response. So basically, your time domain analysis will be studying the transient state response and the steady state response. Okay. Okay. Another point that can be studied is, which is the important thing that we are going to study in the coming modules as well, that is the stability. Now, what is actually the stability? The stability, by stability, it refers to the output get does not get uncontrollably larger, uncontrollably, does not deviate in an uncontrollable manner, does not deviate in an uncontrollable manner. What's the meaning of that? See, or you can also define the stability as it is the ability of a system to be consistent within the desired value. Okay, so it is not enough to be consistent. Say in this example, the requirement of the system is to provide a 5 volt at its output, but so by the stability, it refers to the fact that how much it is capable of being consistent at 5 volt. That means, say for example, sometimes you may be, when you look at the digital voltmeter, you can see reading like this 4 point. When you measure the output, you can find something like this 4.8. For some time it will be 4.9, then 4.8. It goes on. That means it has a slight variation. It's oscillating, but it is controllable, right? It's not deviating in an uncontrollable manner. So you can approximate that to be a stable system, or you can consider that as a stable system. But say, look at the scenario. Say You are expecting a 5 volt at the output, but you are getting a graph like this. What's the meaning of this? The output is the deviation is uncontrollable. The deviation of the output is uncontrollable, which means that such a system is an unstable system. Now, even if it is straight line, say you are getting a 3 volt, still it is an unstable system because the required one is 5 volt. It is not the question whether it is straight or not. The deviation from the decide. If it is decided to have 5 volt, even if it is a pucka straight line, if it is a 3 volt, if it is providing a 3 volt, then that system will also comes under the category an unstable system. So stability can also be studied and ascertained under time domain analysis. Okay. So hope you got a basic idea regarding time domain analysis. Okay, now let's move on to the next topic, that is the test signals. What are the various test signals? And this we have already dealt in, we studied in signals and systems. Okay, now the number one is step signal. Okay, I'll just have a recap of all these things which we have studied. Now, how is it defined? Step signal is usually represented by the letter u of t, which is equal to k for t greater than or equal to 0, and it is equal to 0 otherwise, right? Now, when k is equal to 1, this is called as a unit step signal. Okay. Now, what happens when this? How is it graphically represented? When it is graphically represented as this thing. So it is a constant function throughout the time axis. This is time, and this is actually your u of t. So this is your step signal. When k is equal to 1, it's called as a unit step signal, and it is also called as the displacement signal. The signal is also called as a displacement signal. And one more point to be noted is its its Laplace transform. That is, when you take the Laplace transform of this function u of t, you are going to get this as 1 by s. So the Laplace transform of u of t is 1 by s. Okay, so it is also called as the displacement input signal. This one is displacement input signal. Okay, is it clear? Now coming to the second point, second one is a RAM signal. That's a RAM signal, and you know what it is. RAM signal is actually equal to, it is denoted by the letter r of t, and it is equal to k into t as t greater than or equal to 0. So when k is equal to 1, this is called as a unit step signal. When k is equal to 1, it is called as a unit RAM signal, not step signal, unit RAM signal. Now, what about the pictorial representation? So anyway, this is actually equal to y is equal to mx plus c. Now here c is equal to 0, that means it is y-intercept is equal to 0. So it is the line passing through the origin on the positive half. So this is t, this one is r of t, and this is, when this is 45 degree, that is k is actually equal to tan theta, right? And this is the angle theta. Now when theta is equal to 45 degree, k becomes equal to 1. So 45 degree angle RAM signal is what is called as a unit RAM signal. So its slope is equal to 1. Here the amplitude is equal to 1. Here the slope is equal to 1. And this input is also called as the velocity input. Okay, it is also called as a velocity input, right? This is very important. Now okay, so this is velocity input. And what is the Laplace transform of this? When you take the Laplace transform of a unit step signal, you're going to get this as 1 by s square. Okay, so this is an important thing. Laplace transform of r of t is 1 by a square. And coming to the third point, which we call as the parabolic input. Okay, now the parabolic input is usually represented by P of t. P of t is equal to k into t square by 2. And as usual, when k is equal to 1, we will call this as a unit parabolic input. Unit parabolic input. And this parabolic input can be represented, graphically represented like this. So this is how it looks like. So this is t and this is P of t. Right. Now this signal is also called as the acceleration input. Acceleration input, right? So acceleration input, and when you take the Laplace transform of this, when you take the Laplace transform of P of t is will be equal to k into t squared. Now when k is equal to 1, you are assuming it has a unit parabolic signal. So this will be, when you take the Laplace transform of t squared by 2, you can prove this as 1 by s cube. So this is another important aspect. So this is 1 by s cube. So look at this. Now look at this. So unit step signal is also called as a step signal, is usually called as a displacement input signal. Ramp signal is called as a velocity input signal, while parabolic input signal is called as a acceleration input signal. This knowledge is we require when we study about the steady state error. Okay, now I'll just give you another relationship that exists between these signals. Say what happens when you integrate actually u of t dt, that is u of t dt. When you integrate this, that is 1 into dt, you are going to get this as t, right? This is t. So what happens when you integrate a unit step, and that you are going to get a ramp input. Okay, now if I am again continuing my integration, say I am integrating t dt, that is I am integrating a unit ramp signal. So what's going to be my result? This is going to be, right, this is going to be t square by 2. And what is this? This is actually your parabolic input, right? So from this you can have a relationship like this. When you integrating u of t will give you r of t, and integrating r of t will be giving you p of t. Or in the reverse way, you can say that what is dp by dt? When you take the derivative of dp by dt, you will get r of t, and when you get the derivative of r of t, you will get the u of t. Okay, hope you understand. Okay, now the next one is you have a unit impulse signal. Okay, so I have explained this when we studied signals and systems in a much broader way. So I'm not going to explain too much on this. So it is usually represented by del of t, and del of t is actually defined as it is equal to minus infinity to plus infinity, which is equal to 1 at t is equal to 0. That means, as I told you at that time when we were studying signals and systems, this always refers to an area of a pulse, a short duration pulse. Impulse means it's a short duration force, and it can be considered as a say what a rectangular pulse with the pulse width t, capital T, and the amplitude is 1 by t. As t decreases, that means as it becomes narrower and narrower pulses, the t decreases, and as t approaches to 0, now as the t decreases, 1 by t increases. Still, even then, in both the cases, the area is equal to 1. That's the meaning of this. So this is a very short duration signal whose area is equal to 1. So that's the difference between an impulse signal and all other signals. In all other signals, the strength is assessed by its magnitude, while in the unit impulse signal, it is assessed by its area, not the magnitude. Why? The magnitude goes to infinity because 1 by t is that magnitude, and as t tends to 0, 1 by t tends to infinity. That means it is going to have a high amplitude, or it can reach up to infinity, but still the area of that pulse is equal to 0, is equal to 1, and it is equal to 0 at elsewhere, right? At all other points this is going to be equal to 0. Now usually this, in a time domain, we represent del of t in this way, del of t as by an arrow. This is an ideal del of t. Okay, so that means that shows that the arrow shows that the magnitude goes to infinity, but the area of that pulse is equal to 1. Okay, now what is the Laplace transform of this? Laplace transform of del of t is nothing but it is equal to 1. Okay, so this is also an important aspect. So that's it. Now let's move on to the next topic, that is the transient response. And as I've mentioned here, the transient response of a system is the total response can be can be divided into two sections. What is the one is the transient state response, and the other is the steady state response. So it is actually the response till it reaches the steady state, and it can dictate how fast a system can arrive at the steady state and all other informations. And other than that, you will get a lot of informations from those transient response. Okay, now we'll be dealing some of the important informations regarding the transient response from the transfer function. Okay, from the transfer function of a closed loop system. Okay, of a closed loop system. For that, consider a general closed loop system as shown in the figure. Okay, now consider this block diagram, which is the simplest, or this is the canonical form of a closed loop system with a G and H and a summing point. We know the transfer function to be, which is equal to C of S by R of S is equal to GS by 1 plus GS H of S. So this is actually the transfer function of a system. Now say if you have this thing, okay, right? So from this you will be able to get C of S. What is that? So this will be R of S into G of S by 1 plus GSHS. Okay, so you will be getting a function of S domain, or this can be treated as some P of S but to Q of S form. Now from this, if you can find the inverse of this, you will get the Laplace inverse of. Okay, so this is the Laplace inverse of what? Laplace inverse of R of S into G of S by 1 plus GS HS. Okay, so you'll be getting C of t, right? Now this is what is called as a response, right? The C of t is called as a response, or this is what is called as a time domain response. Time domain response. And it is about this response that we talked about. That is, this response consists of a transient state response and steady state response. And when you analyze this carefully, you will be able to distinguish these two responses. Okay, as the time increases, or as the time increases, right? We can see that a system transit from the system will be in a transient response, and finally it comes into the steady state response, or the desired output. Okay, now let's move on to zeros and poles. Now, in order to study about zeros and poles, we have already dealt in signals and system. We require a transfer function, right? Now we know the transfer function to be equal to GS by 1 plus GS by 1 plus GS HS, right? This is your transfer function. Okay, this is of the form P of S to Q of S. Now we know that when P of S is equated to 0, and if you solve this polynomial when it is equated to 0, you will get some roots. Say, let us denote that as z11, z2, etc., and it depends on the degree of the polynomial P of S. And these roots we call as the zeros. Why they are called as zeros? Because at these points the transfer function becomes equal to 0. Now similarly, when Q of S is equated to 0, you will get some points like P1, P2, P3, etc., which are called as the poles of the system. Now at the poles, what happens to the transfer function means transfer function becomes infinity. So at these 2 points, that is at zeros and at poles, the network function will be having a value either 0 or it's either null or it's infinity. That is that means this actually, if there would not been any zeros, then the transfer function will not exist even. Okay, so transfer function will always be a constant, and transfer function has to be a function of S. That means it should vary. Then only we can analyze that, and the zeros and the existence of zeros and poles makes it beautiful, makes the transfer function analyzable. So you can call this the backbone of the transfer function is, or the network function is, zeros and poles. Right. Now, let's move on to further. So, this is Z1, Z2, all these are called as. Now, coming to the transfer function, now we will be concentrating more on these poles, and you will understand why we are more concentrating on the poles of a system. Now, if Q of S is equated to 0, meaning if that in the transfer function, if you equate 1 plus GSHS it's a polynomial, so 1 plus GSHS is going to be another polynomial. When it is equated to 0, this becomes an equation called as the characteristic equation of the system. Characteristic equation of the system. And when you solve this, you will get what? You will get poles in the form of P1, P2, up to how many poles? It is equal to the number of degree, the degree of this equation or this polynomial. Now, these poles and the zeros, you can say similarly when you equate P of S to 0, you will get Z1, Z2, etc. So these poles and zeros are generally called as the critical frequencies. Okay, now these are called as a critical frequencies because it is the value of S, right? Now, why it is called as critical frequency? Why it is called as frequency? Because these Z1, Z2 or P1, P2 are the values that you obtain for the S variable. Now, what is generally S? S is defined as sigma plus j omega. So sigma is called as the frequency in Nepper, okay, while omega is called as a frequency in radians. And we are very much from the stability point of view, we'll be interested in the sigma value, and that also you will understand later. Okay, so sigma is the frequency in Nepper frequency, while omega is the frequency in radian. Oh, hence this is called as a radian frequency. Okay, right? Okay, and these poles are called as the closed loop poles. Closed loop poles. Okay, now generally this transfer function can be generalized as I mentioned earlier, it can be generalized as P of S to Q of S, or this can be represented as M into S raised to M plus M minus 1 S raised to M minus 1, etc. up to E0. That means where M is the mth order polynomial, P of S is going to be the mth order polynomial, and Q of S be let it be bn, so that this becomes s raised to n plus bn minus 1 s raised to n minus 1 plus etc. up to b0, or okay, now this is it. So you can represent this as a polynomial, as a ratio of two polynomials as shown. Okay, now if you have m poles, you can solve these p of s and q of s, and imagine that the so p of s, when it is equated to 0, these are the poles, z1 z2, these zeros. Well, when q of s is equated to 0, you will be getting p1 p2 etc. So the same expression can be written as now if I take this a raised to m, okay, a raised to am and bn, so I can rewrite this in say some constant. If I take am bm, so this becomes s raised to m plus am minus 1 by am, s raised to m minus 1 etc. by plus a0 by am and bn. Okay, so that am by, so I'll do it for you, am by bn. So when you equate this, you will get this as s raised to m plus am minus 1 by am, s raised to m minus 1 etc. up to a naught by am, right, divided by, what about this? This is again s raised to n plus s raised to n minus, sorry, bn minus 1 by bn s, s raised to n minus 1 etc. up to b0 by bn, right? Okay, so this am by bn can be written as a k, which is called as a scale factor. So k into s minus, so the other thing can be written as is s into s minus z1 by s minus z2 etc. divided by s minus p1 into s minus p2 into etc. Okay,